Each of these. Gravity, I think most
Gravity,
people
I think people know
when
about.
you drop something. Electroweak is electromagnetic, and some nuclear force.
The weak interaction, which is the hardest one to grasp, it's when a neutron decays to a proton, electron, and neutrino, for instance.
Let's keep it basic. When we deal with the electromagnetic, is electricity and magnetism combined together, and weak is something in the nucleus.
And those were combined in a very elegant theory. And then the third one is quantum chromodynamics that binds the quarks together inside a proton or a neutron.
Okay, now we're going to have to define
strong force.
Strong, very strong. Gluons that bind them together.
All right, let's now define what a quark is. Steve, you want to?
A quark is, as far as we know, one of the elementary building blocks of protons, neutrons, mesons, the stuff that is most of the matter in the universe, all right?
How many are there?
There are 6, and they come in different colors. They come in 3 different colors. They come in 6 flavors. They have spin. They spin around like a little top, and the spin can be up like that or down like that.
And now we have to get what is commonly called a theory of everything. Is that the TOE? Is that TOE? Now, what do we have to add to that, Greg?
Wow, lots. That is, you have to stitch all of this fabric together and somehow make a suit that people want to wear. And I've been, in fact, thinking about that a lot because I don't work in the field, but so I'm sort of an informed skeptic about it. And the current the hot topic is, of course, string theory. It's a great field.
This is not about bikinis,
no,
is it?
It's not about bikinis, I don't think.
Okay.
Just wait, though. In just a little while, Leon will have a line about that ready for it.
The main string theorists cluster around Princeton. There were 4 great guys, and they're called the Princeton String Quartet.
Yes. Ed Witten et al.
He's the leader. He's the leader.
Right.
String quartet's not supposed to have a leader, but that's all right.
This is a string quartet with a leader.
Yeah. I think it's certainly the most complex physical theory ever advanced. And you can tell that because all these brilliant people are having a visibly difficult time with it, which is encouraging. That is, a really great theory that tells us everything ought to be really hard. And it should not come to one person in a weekend. And that's the best clue that we may be on the track of something very large. But what we're on the track of is still, I think, very mysterious. The idea that particles are not little dots, but they're strings that vibrate. Lies at the core of this. Of course, that's another chimpanzee metaphor. But the implications of it are huge. It goes everywhere from Andre's cosmology to the fundamental way that you glue all these particles, as we think of them, together.
One of the key problems with the Standard Model, as he said, 6 quarks, 6 leptons. The quarks come in 3 colors, and they come in anti-quarks, so there's something like 36. In some sense, if you try, and it's a powerful theory. The Standard Model explains all the data coming out of all the accelerators since Galileo dropped these 2 students off the Leaning Tower. A fat student and a... Well, gravity sits there as one of the problems. Gravity has not been incorporated gracefully into the Standard Model, and the Standard Model by itself, first of all, aesthetically, it's ugly. The Greeks promised us beautiful simplicity, a beauty and an elegance, and we don't have it. We can't even fit all these particles on a T-shirt.
Leon, the Standard Model, though, is incredibly elegant compared to what preceded it in the 1960s, which was a mess.
It's a powerful synthesis.
It's a powerful synthesis, but then it raises the next question.
We want a T-shirt with one thing on it, gloop. And that does everything.
The theory of everything.
You know, we've seen this pattern repeat over and over in science. Look at the periodic table, right? In the 19th century, when people were organizing the elements, all right? It was a mess, all right? There were 90-some-odd elements, and you really couldn't understand that there was nothing you could put on your T-shirt.
Right.
And then in the early part of the 20th century, we had that one thing in it.
A
it was quantum
unifying
mechanics,
theme.
right? And
That's right.
similarly with
the
quarks
Standard Model is the physicist's version of the periodic table.
That's right.
And our belief in simplicity and elegance and not disappointed over the centuries in which we've done this science tells us there's something simpler.
100 years from now, will there be a theory of everything that will be complete, unassailable, and forever immutable? And I can't think of a better person to start.
Immutable.
10-second answer.
Yes.
Okay.
Yes.
Andre, what do you think?
No, I don't think so.
I think so. You look at where we've come in the last 100 years, and I would guess yes.
Greg?
I believe so, but remember, even the theory of everything won't actually tell you everything you can ask.
No, that's one subject that you're asking
Sure,
about,
sure.
not a traffic jam in Chicago or the common cold
right.
or some of these complex things.
Well,
That's different.
why you wore that tie.
Yeah, exactly.
I think there will be a theory of everything that we understand or that we observe now, but it's very likely that we will observe new things that won't quite fit into that theory, and then we'll be back to where we are right now. That's one of the joys of science.
So there'll still be a purpose for the show.
Indeed,
Okay,
indeed.
good.
We'll be closer.
Yeah. The great mystery of quantum physics is that it works. Really weird stuff at the subatomic level forms rather ordinary stuff at the human level. But the standard model isn't complete. Gravity must join with electromagnetic and nuclear forces to yield a theory of everything, the holy grail of physics. The best current idea envisions mystical, minuscule superstrings whose vibrations may make the universe sing. It gives a chill to reach so deeply into reality. But if you're unconvinced, you're in good company. Albert Einstein didn't believe quantum physics either, which just proves how hard it is sometimes to get close to the truth. I'm Robert Kuhn.